Arnold has two PhD degrees. First is from the University of Bordeaux, where he focused on lasers, materials, and nanosciences. And second PhD degrees is from the University of Florida and is from optics. He is co-founder and also chief technology IT department of Argolight company. Yeah, please, you can start.
Thank you for the introduction. Can you hear me well? Can you hear me?
Yes.
Yes. Okay, perfect. Thank you for this nice introduction. So I work at Argolight. For those who do not know us, we are a French company located in close to Bordeaux in the southwest of France. And we basically design, manufacture, and commercialize tools, both hardware and software, for the quality control and the quality assessments of fluorescence imaging systems. And today I would like to talk to you about how to measure resolution in diffraction limited and super resolution fluorescence microscope. All right. So when we talk about resolution, what do we mean exactly? So I did a little literature review and I found some interesting papers. For example, in 2013, Kramer and Master stated that in classical light microscopy, the resolution is related to the capability of displaying detail in an image. The term resolving power in microscope refers to the ability to distinguish in the image 2 points that are in close proximity in the object. And third important thing they state in this paper is that the concept of resolution is ambiguous because different authors interpret resolution in a variety of ways. Jonkman and co-authors in 2003 defined resolution as the minimum separation between 2-point objects such that they can switch. However, they say that there is some ambiguity as to what constitutes this minimum separation, and therefore they propose to quantify resolution to define the term of contrast. In 2016, Ostermeyer and authors basically define resolution in many ways. First one is that it can be quantified by measuring the intensity point spread function, so the IPSF, of the microscope and stating well-known features of it, such as the distance to the first minimum, it's called the Rayleigh limit, or the distance at which two adjacent PSF show no intermediate D, that is called Sparrow limits, or the highest spatial frequency. And they state also that the Fourier transform of the PSF, known as the optical transfer function, is another common numerical. So here we can see from this article that there are actually many ways to define resolution. And to conclude, I would like also to quote Shepard in 2021, who also state that there are many ways to define resolution, but what is a sentence that I found very interesting and that said that the fact that we are better than the resolution limit, and he meant by that super resolution, this suggests that resolution is not an inherent property of an optical system, and instead the optical system has the capacity to transmit a finite amount of information. So that's all for the literature review. You can eventually go deeper by taking a look at this book, where there are actually even more ways to define resolution. So there's a single point resolution, the 2-point resolution, but also the single line resolution, 2-line resolution, and finally the optical transfer function approach. So which one is the best? Well, it depends on the application. It will depend on the biological sample you want to image. If you would like to image filaments, then the single line resolution approach would be more relevant. While if you want to image thick cellular objects, maybe the optical transfer function is the most relevant. So the best approach really depends on the application you have become. So why do we focus on resolution? Why resolution is so important? Well, because it's a determining factor of image quality. Many vendors say that seeing is pelleting, make it visible. Now we can see seeing is solving. Because resolution allows to see features with a good contrast. If I want to count objects, then I need to have a good resolution to separate those objects. In colocalization experiments, the spatial resolution of the system defines basically the scale of the experiment. If you want to deconvolve image, it's better to acquire ESF of your imaging system. And I'm sure I forgot many other applications. And that is why resolution is one of the main metrics, if not the main, for microscope performance assessment and monitoring. So during this talk, I will talk about three different approaches to measure the resolution. The first one, I will first talk about the two-point approach, which defines the resolution by the radius of the first luminal BRDs. I will then present the single-point approach, which defines resolution by the full width and half maximum of the point stretch function. I will then talk about the optical transfunction approach, which defines resolution by the highest spatial frequency supported by the imaging system. Because it is out of my competencies, I will not define resolution via Heisenberg's uncertainty principle. I will then show how these three approaches relate from one to another. I will present the different parameters influencing resolution. I will show how, with our tools, we measure resolution. And then I will present some remarkable results we can obtain with Argolight's approach. Okay, let's start with the two-point approach. So the concept of the two-point approach is basically to consider 2 point sources separated by a small distance and emitting mutually fluorescence. So what exactly is a point source? It's basically a point or an object that has the size, which is about half of the theoretical resolution of the microscope. And within this approach, 2 points are considered as resolved. They can be separated by a clear dip in intensity when imaged by a specific microscope. But what is actually a clear dip? And this is quite a subjective notion. And this is why we introduced the term of contrast to quantify this dip. Contrast is defined according to this formula here. And in the two-point approach, there are several contrast criteria. So the most well-known is the Rayleigh criterion. Within this criterion, the contrast is set as 26.5%, and the theoretical formula to calculate the distance between the two-point object is given by 0.61 lambda over NA. But there is also the Sparrow criterion with a contrast of 0% and a coefficient of 0.47. And also the Chester criterion, for which the contrast is 100% and the coefficient is 1.20. So basically, within this approach, we base the resolution measurement of the spacing measurement between two close point-like objects. And the lateral resolution is basically defined as the measurable distance for which the two close point-like objects are distinguishable, but for a given contrast. So the measurable distance should be accompanied by a value of contrast to make the measurement complete. How do we do to measure the resolution within the two-point approach? Well, we can use DNA nanorulers that are actually point sources separated by a controlled distance. So we image those nanorulers. Here's an example of nanorulers made with the Eriscan microscope from Zeiss. Here, the nanorulers are 120 nanometers. And you draw a intensity line profile, and you measure the distance between the two peaks, and you measure the associated contrast. What is important to note is that for this kind of sample, the resolution, that is the measured spacing, is valid only for a single contrast. If you want to have access to more spacing and contrast measurements, then you need more samples like this with different spaces. All right, let's continue with the single point approach. The concept is very simple. So it is to consider one point-like object emitting fluorescence. Again, a point-like object, point source It has a much smaller size than the resolution of the system. And of course, as you know, the image of such an object is the point spread function of the microscope, which basically describes how the light spreads from a point source. And to measure the resolution, basically you draw intensity line profiles and you measure the full width at half maximum of the lateral PSF. And in that case, the theoretical full width at half maximum is given by this formula with a coefficient of 0.515. To measure the resolution within the single point approach, you can use sub-resolution fluorescent beads. So you image those beads, you will have many beads in your field of views. You select one bead. Here are the orthogonal views of the bead. You draw an intensity line profile and you measure the full width at maximum using usually a Gaussian function as a fitting function. There are many softwares that allows you to do that, to extract the full width at half maximum of PSFs. And some of them can do that only on one bead, and others like Metrology QC or PSFJ can do that on many beads in the field of view, so that you can average and get statistics. Although this approach looks quite simple, there are actually many pitfalls that should be looked carefully. And these pitfalls have been emphasized by the ISO group working on confocal microscope optical data, and also from the Crowell eye, and in particular from the working group 5 working on natural and external resolution. For those who do not know, the Crowell eye is an international endeavor to try to make fluorescence data more reproducible, and that is focused on the quality control and quality assessment of the fluorescence imaging system. So among these pitfalls, they have the detection of the beads. You need to define carefully the threshold, and you need to measure accurately the centroid position. Actually, depending on the fitting function you're going to use, you may get different results. Also, there are some simple functions like the symmetric Gaussian, but you can make it a little bit more complex using an asymmetric function. And you can also fit the PSF using 3 times one-dimensional fitting functions, but you can also fit, you can use the 2D fitting XY plane in the 1D fit Z plane, or you can even use a 3-dimensional solution. The fitting method has also an importance, whether you use the least squares or the maximum likelihood estimation approaches. Preparing the sample is very important, as you may think. How you prepare the sample, for example, what size for the beads you're going to use, what mounting medium, what protocol you're going to follow, and who also is going to prepare these beads. Does he have the ability to follow probability protocols, or does he know how to use properly your microscope? And finally, the acquisition parameters are also very important to get accurate measurements of the full width at half maximum of the PSF. For example, the signal to background ratio, signal is ratio of importance, and of course, the pixel size as well is very important. The third approach I would like to talk about is the optical transfer function. So behind this concept of optical transfer function, there is the fact that contrast is actually as essential to the production of an image as what we usually call resolution. And indeed, the two concepts are very close or correlated, or can be thought of in terms of each other. And they can be linked by what we call a contrast transfer function. So quite simply, it's a graph that plots the contrast versus the size of some features in an image, or it can be also plotted instead of using the spacings, the spatial frequencies of the features in the image. In that case, the lateral resolution is the cutoff frequency of the contrast transfer function. This is called the upper limit, and it's given by this equation with a coefficient of 0.5. There are several ways to measure the contrast transfer function. One of them is to use fluorescent gratings having different periods and orientations. For each grating, spatial frequency or an intensity line profile. For each grating, you will measure the contrast. And then you will plot for each frequency, the contrast, and you get the contrast transfer function, as you can see here on the right. And as expected, so here are the three contrast transfer functions for three different objectives, from low numerical aperture to high numerical aperture. And as you expect, the objective that has the highest numerical aperture has the highest spatial frequency, the highest cutoff frequency. Because the contrast transfer function using what we call Siemens star, there is a picture of a Siemens star here on the left. Basically, the approach is quite similar. It consists in plotting profiles along different arcs, circle arcs, and you will measure the contrast for each spatial frequency, and we will reconstruct like this contrast transfer function and measure the cutoff frequency. The bad news here is that both these samples are not commercially available or not well suited for typical confocal or super resolution microscope, because the gratings, they have a large period. The gratings that are commercially available have a large period, and the Siemens star was actually a lab prototype and was never commercial. If you want to find more information, you can have a look at this page. How do these three approaches relate? Well, it's quite simple for the point spectrum function and for the contrast transfer function. They basically are related via the Fourier transform. You can relate the one-point approach, the single-point approach, and the two-point approach if you consider two-point objects that are separated by a distance equivalent to the full width at half maximum of the point stretch function. And if you have access to several samples having key points that are spaced by different spacings, then you can reconstruct a contrast transfer function. However, this relationship are valid only for an ideal perfect fluorescence imaging system. And by ideal, I mean there is no optical aberration, there is no noise, no background in the image, the sampling rate is infinite, and as well as dynamic range. And basically, if you want to compare theoretically what the different criteria within the two-point approach compare, then you can have a look at this table here, where for different contrasts, we have the theoretical resolution here, the associated contrast here, and here you have the relative variation from one criterion with respect to the Houston criterion, which is the full width half maximum of the PS. And you can see that you can have a difference of about 137%, depending on what criterion you choose. Okay, now let's talk about the different parameters influencing resolution. Well, actually, there are many parameters. Of course, there's the acquisition modality, whether your microscope is a wide field or confocal, for example. The wavelengths, both the excitation and or the emission of them. And of course, the objective numerical aperture. You have the optical aberrations as well that affect the resolution. Mainly the spherical aberration affect the resolution, and this aberration can be due to refractive index mismatch or for example, from a poorly adjusted correction color. Another parameter that is usually forgotten is the polarization. In microscopes equipped with the polarized light sources, the resolution varies depending on if the polarization is linear or circular, or even vertically or linearly polarized or horizontally linearly polarized. In confocal microscopes, the pinhole diameter and alignment has an influence. And basically, all these parameters will define the K coefficient in front of the ratio lambda over LA in the theoretical formula. There are other parameters like background, from out of focus fluorescence or autofluorescence, the noise, the pixelation, that is the fact that the images are pixelated and analog continuous, and the detector bit depth or the image dynamic range influence the resolution. When we deal with post-acquisition processing parameters, such as the convolution or seam reconstruction, we can have an effect on the resolution, of course. And to finish, there's the sample type and size, like the bit size or the line width, the thickness of the sample, the longitude, median, and so on. Among all these parameters, there are some that can be set and frozen once and for all. They appear in green and in gray. But the other parameters can usually be adjusted either in the acquisition software or in the processing software. Okay, so let's have a deeper look in each of these parameters. Let's start with the polarization. In this publication from Jonkman and co-authors, they simulated the PSF of a confocal microscope. As a reminder, the PSF of a confocal microscope is the product of the illumination PSF with the detection PSF. Here you can see the orientation of the polarization, which was along X. The first picture here is the illumination PSF along XZ. The second here is the illumination PSF along YZ. Here, the third picture here is the detection PSF, and here you have the product of the illumination PSF by the detection PSF. Here on the right, you can see the parameters used for the simulations. And basically, what they found out is that the full width at half maximum of the PSF along the polarization is larger than the full width at half maximum perpendicular to the polarization. And if you want to quantify that, there is about 30% of difference in the illumination PSF, resulting in about 17% of difference in the confocal PSF. This inverter has been experimentally demonstrated by Lee and co-authors. So they imaged gold beads using confocal microscope and different polarization, both linear and circular. For the linear polarization, they measured the difference of about 100 nanometers. Depending on the axis. When they rotated the linear polarization, they saw that the anisotropy of the full width at half maximum followed this rotation, and when they used circular polarization, they found exactly the same full width at half maximum along X and along the Y. And if you do the calculation, they experimentally found the same value as it was simulated, about 30% for the illumination PSF. And not that because they used only gold, they used gold beads. They measured the illumination PSF and not the overall PSF of the microscope. The pinhole has an influence on the resolution, as you probably know, as you increase the pinhole above 1 area unit, has no influence on the resolution, although more signal reaches the detector. So as a result, you get an increase of SNR and SBR. If you decrease the pinhole diameter below 1 area unit, then you get a resolution improvement, but less signal reaches the detector. So as a result, you get a decrease of the SNR and the SBR. Actually, if you close the pinhole down to its smallest value, you can have an increase of resolution of about 1.4. But there is actually an optimum in terms of resolution and signal at about 0.63 area units, for which you have a gain of resolution of about 1.1 and a decrease of the signal of about only 10%. The contrast, of course, has an influence on the resolvable distance, as we discussed earlier. There are many contrast criteria to define resolution: the Schuster, the Rayleigh, the Sparrow, and of course, depending on the chosen contrast criteria, the resolution change. Actually, any contrast between 0 and 100% can be considered to define resolution. 1998, Stelzer wrote a very nice paper gathering all different parameters influencing contrast and resolution. And basically, he simulated 2 point-like objects separated by the distance equivalent to the Rayleigh criterion. He added some noise. He pixelated the profile, and he added the two contributions. And what we see is that noise reduces the contrast, pixelation reduces the contrast, and both have an effect on the resolution by decreasing it. I'm not showing data, but in the same paper, he showed that image dynamic range also has an influence on the contrast. The higher the dynamic range, the higher the contrast. It's clear. In another paper from the University of Basel, Terran co-authors basically qualitatively investigated the influence of SNR and SBR on an image on the resolution. So they image this biological sample. They plot a line profile here, and they acquired 3 different images: one with a reference SBR and SNR, one with a low SBR, and one with a low SNR. So for the reference image, you can see that they can clearly discriminate 2 features here. When the SBR is low, the contrast is decreased, but 2 features can still be discriminated. But when the signal-to-noise ratio is low, the 2 features can no longer be discriminated. So signal-to-background ratio does not influence resolution. This is actually not exactly true, as the contrast is decreased. And signal-to-noise ratio does influence resolution. If we have a careful look at the influence of signal-to-noise ratio on the PSF full width at arc maximum, we can read this paper from Li and Wang. They simulated data from a single spot with a 200 nanometer PSF full width at arc maximum, and they simulated this PSF with the different signal-to-noise ratio in the image. Here you have an example for a signal-to-noise ratio of 5, and here you have an example for a signal-to-noise ratio of 50. What we can see in this plot here is that the PSF width at arc maximum decreases as the SNR increases, and they found out that there is that you need an SNR of about 50 to find the expected full width at arc maximum. So the explanation, the resolvable distance. They simulated 2 point-like objects separated by distance equivalent to 30% of contrast. and they changed the pixel size from 1 nanometer to 50 to 100 up to 175 nanometer. And here you can see that the 2 points of the profile and the 2 point can clearly be discriminated, while for a high pixel size, it's no longer the case. So the contrast decreases, the pixel size increases. The Nyquist sampling distance was about 150 nanometers in those simulations, equivalent to a contrast of 10%. And their conclusion was that to preserve the contrast, a sampling period of about 1/3 of the theoretical resolution is necessary. So to recap, resolution is a multi-parameter feature. As we saw, noise, background, pixelation, dynamic range influence the contrast and the accuracy of fit. And these two parameters, contrast and accuracy of fit, influence the resolvable distance we can achieve. And actually, all these parameters are gathered in what we call the resolution. How do we measure the resolution with Argolight's tools? We have designed a pattern, a fluorescent pattern that we call the gradually spaced lines. Basically consists of pairs of lines that are more and more spaced, as you can see in the image here. In that case, the two inner lines are not resolved, while in this on the other side of the image, you can see that the two inner pairs of lines can be resolved. We have two models of slides. One is called the Argolight with these spacing values here from 100 to 700 nanometers with a step of 50 nanometers. And we have also a slide that is called the Argosyn that has steps ranging from spacing ranging from 0 to 390 nanometers with a step of 30 nanometers. And we're going to use this gradually spaced line pattern with our analysis software that is called Daybook. And this is how we extract the resolution measurement. The approach we use has been widely inspired by this article from Kolocalization and co-authors. So how does it work? Basically, so we acquire an image of the gradually spaced lines. We draw an intensity line profile perpendicular to the lines. The width of the region of interest is about 1/4 of the length of the lines. Is what we get. Then we detect the peaks and the valley between the two inner lines in order to measure the contrast for each group of lines. Okay, so the contrast is given by this formula. It's the average of the four peaks minus the valley density divided by the parameters. So at the end, we get several contrast measurements for each line group index. On the other end, we fit for each group of lines the profile using Gaussian or Lorentzian function, and we measure the actual spacing between the two inner lines, and we do it for each group of lines. And measured line spacing versus the line index. So we gather these two measurements, the measured line spacing and the measured contrast, and we plot the contrast transfer function, which you get, and you can see an example here on the right. One of the strengths of this approach is that using the same image within the same algorithm, we can actually also extract the signal-to-noise ratio in the image. How do we do that? We draw intensity line profile along the outer lines of each group of lines. We get this kind of plots that are the sum of the signal and the noise. We say that the signal is the average of the line profile, and the noise is the standard deviation of the line profile. And we average the signal and the standard deviation, and we do the ratio of one to another, and we get the signal to noise ratio. And the signal to noise ratio is close to what is usually done, as you can see in this Wikipedia page. It's the definition that is the closest as what is usually used, for example, in the telecommunications physics. And also, we can measure the signal to background ratio. So the measurement is more simple. We measure the mean signal, we measure the mean background outside the pattern, and we divide one by the other. So for with only one image, you can have access to the contrast transfer function, to the signal to noise ratio, and to the signal to background ratio. And as we saw earlier, signal to noise and signal to background ratio influence the resolution. So to validate our approach, we tested both a simulated and a real image. A simulated perfect image without any noise, without any background, dynamic range of 16 bits, and actual pixel size of 65 nanometers. And in the real image, of course, you have noise and you have background. So for the simulated image, a very nice and very smooth contrast transfer function with an SNR and SBR that are infinite. For the real image, we get a less contrasted contrast transfer function as expected with the finite SNR and SBR. So our approach works quite well. It's quite robust, and we can use it on different configurations, or with different imaging systems, or different imaging modalities. For example, we have used this pattern to measure the evolution of the resolution when we adjust the pinhole diameter. So we acquired several images of horizontal graduated spacelines from 0.2 to 3 area units. We processed all these images using our software, and here I'm showing you only a few contrast transfer function for this for pinhole diameters. As expected, the contrast increases as the pinhole size decreases, and as well, the minimum resolvable distance decreases as the pinhole size decreases. So as expected, decreasing the pinhole size leads to an increase in the contrast for the same line spaces, and therefore to an improvement of the resolvable distance. Also measured the evolution of the signal to noise ratio and signal to background ratio. And as you can see here, we get the same sigmoid evolution for the resolvable distance, both for the Rayleigh criterion or for the 0% contrast criterion. We see as well as the SNR and SBR follow this sigmoid evolution. And to the best of our knowledge, I think this is the first time that this kind of curve is experimentally demonstrated. We can also quantify the gain in resolution when the gradually spaced lines are imaged with fence.
Okay, Arno, we have to finish your talk.
Yeah, I have 2 more slides.
Yeah, okay.
So we acquired images of the gradually spaced lines using wide field image. We deconvolved these images, and we use also SIM and SIM square modalities. Process these images and superimpose the contrast and point function. And as expected, for the same spacing, the contrast increases with the processing method. And as expected, the resolvable distances decreases with the processing method. So we can actually quantify the gain in contrast and the gain in measurable distance from one imaging modality to another. So to conclude, I presented you 3 approaches to measure the resolution. based on the full width at half maximum of the PSF, or the resolvable distance between 2 points for a given contrast, or from the optical transfer function. We have reviewed the parameters influencing the measurement. The presented approaches have their own advantages and drawbacks: samples availability, community habit, and acceptance. Some approaches can measure computationally enhanced resolution, others cannot. And for diffraction limiting microscopy, but also for super resolution microscopy, there are actually many other parameters that are important to characterize the microscope. So, for example, in SIM, there are the reconstruction artifacts, but there's also, for any microscope, the coordination inaccuracies, three-dimensional issues, the field non-uniformity, the field distortion, etc. With that, I thank you for your attention.
Thank you again. And now questions, but I think that we have question from 100% participant.
Yes, there's a question from our virtual participant. Is there a way to account for sample refractive index while analyzing Argolight patterns, e.g. by entering a range of values in the analysis software and visualize how it affects resolution, signal-to-noise ratio, and so on?
So actually, no, it's not possible. The gradually spaced line patterns, they are engraved inside a glass that has the same refractive index of microscope cover slip with and they are 170 micron below the glass surface. So they are they actually can be used to evaluate the performance of microscope in the conditions they are actually designed for. If you want to measure the influence of the immersion refractive index on the resolution, then you can change the immersion medium, and of course we get a degradation of the performance in terms of spherical aberration and signal-to-noise ratio and so.
Do you have any questions? Yeah, please.
Hi. Yeah, thank you for this really lovely talk. I was wondering, from several reports, I've heard that the line spacing profile actually gave often, how to say, too good results. Yeah. So SIM could kind of resolve, 90 nanometers and so forth. So area scan 120, but that's actually too good to be true. Have you heard about this, or can you explain that?
Yes, we heard about this, and the values that have been reported and you just said were reported because the authors or the people who use our slides, they relied on the specified distances that have some manufacturing tolerances, and they didn't use our software, which actually measure the distance between the lines. So there may be some uncertainty in the measurements they did, uncertainties that are taken into account when you use our software, because we actually measure the line spacing.
Okay, maybe, finish. Thank you again for your nice talk, and applause. Yeah. So now